Hey, welcome. Here's the scoop for today. We have been working with some of our basic trig functions, our 6 basic trig functions. We've talked about sine, cosine, tangent, cotangent, secant, and cosecant. And we've used these within right triangles. We've also used their inverses to find angles. But what we want to do now is we want to generalize. And we want to think about these 6 basic trig functions, and we're going to focus on our 3 here for this piece, the sine, the cosine, and the tangent, although the relationship with our other 3 still exists the same as what it did. But we want to extend the idea of those 3 trig functions outside of a right triangle so that we can find the sine, cosine, tangent of angles that are maybe right angles or obtuse or even maybe over 180 degrees, so different things that we want to work with. So the way we're going to do that is we're going to work with what's called the unit circle. So what is the unit circle? Well, the unit circle is the circle, pardon the bell, it's the circle centered at the origin, 0, 0, with a radius of 1. Okay, so if I think of this, and I'm going to draw a picture here in a second, the points on the circle would have 1, 0, 0, 1, negative 1, 0, 0, negative 1, and all the way around. But we think of any point on the circle as a rotation of this starting point, 1, 0, and we rotate that around. So let's take a look at a graph here. Here is our unit circle. There's my unit circle centered at the origin. And what we did is we took this point right here, 1, 0, and we rotated it around and stayed 1 unit away, and we ended up with this nice unit circle. So everything stems off of this point. This is a pretty important point for us. So let's get some of this stuff out of the way, make it a little cleaner for us to look at. And let's go back up to the top here. So how are the sine and cosine related to the coordinates of the image of my starting point under rotation? So first thing I'm going to do is I'm going to say, well, what if I rotated that point 30 degrees? There's my 30-degree rotation. Well, we know that the ratio of a 30, 60, 90 triangle should be 1 to square root of 3. Now, we're inside of a unit circle, so that changes things a little bit, because instead of that hypotenuse being 2, the hypotenuse of our triangle is always going to have a length of 1, because our radius of our circle is 1. Okay, so let's see what happens there then. Let's drop this line down. Let's make this a right triangle. So now I've got a 30, 60, 90 triangle right here in blue. I've got my 30, 60, 90 triangle up here in red to compare to. And since they're similar triangles, the sides should be proportional. So I'm just looking at this and I'm saying, well, my blue triangle is half as big as my red triangle. So that means that this right side should be 1/2. And this bottom side should be square rooted 3 over 2. Well, what that means to me, if I look at this point right here, its x value is square root of 3 over 2, and its y value is 1/2. Now when I compare that to the sine and the cosine of my triangle, let's see my blue triangle, 30 degrees, the sine of 30 degrees, or I could use my red triangle because similar triangles are going to have the same sine. No matter where my 30-degree angle's at, it's always going to have the same sine. So opposite over hypotenuse, sine of 30 degrees is 1/2. Cosine of 30 degrees is square root of 3 over 2. So hopefully we noticed that those are in our point. And what we end up seeing from that is that any point on the unit circle let's call it x comma y. We know that the cosine of that angle that gave us that point is going to be, well, cosine was in our x spot because it was our horizontal change. It's going to be equal to the x of that point. And the sine of the rotation is going to be equal to our y value of that point. Or I could say that any point on the unit circle, let's go back up here and draw another one, any point on the unit circle right here that has a rotation of theta degrees has the coordinates cosine theta, sine theta. And what that does is that allows us to find sines, cosines, and eventually tangents of angles greater than 90 degrees. And what we do to compare that is, well, we just drop down and we make a reference triangle. And we use that reference triangle to help us out with these sines and these cosines. So here, just kind of talking about those reference triangles that I mentioned. So we're looking for sines and cosines of angles that are no longer between 0 and 90. And we use these reference triangles to help us out. So here's an example. Let's say I wanted to find the sine, the cosine, and the tangent of 135 degrees. Yeah, I can use my calculator to approximate that, but I want the exact value of all three of these. So what I'm going to do is I'm going to say, well, I'm going to draw a picture. I start with my point 1, 0. I rotate it around my unit circle. Let's see, 135 degrees. That's 90 plus 45. Okay, so right there, somewhere in between 90 and 180 degrees. Our rotations always go counterclockwise. And I see that, well, if I draw on my reference triangle, I know that that was 45, so that means this one has to be 45. Oh, okay, so let's get a little messy there with all my drawings. Let's kind of erase that arrow, move that out of our way for our rotation. Well, I know in a 45, 45, 90 triangle, it's got a ratio of 1, 1, square root of 2, but since I'm in my unit circle, I need this to be 1. My hypotenuse has to be 1 because it's in my unit circle, so this is going to be 1. And to get from here to here, I can set up proportions, or I can think about what I had to do, and I had to divide by square root of 2. So I'm not going to rationalize these denominators yet. I'm going to say, well, then this side would be 1 over the square root of 2, but it's to the left, so it's negative. This side would be 1 over the square root of 2, and it's still up, so it's positive. Okay, so that means that my point right here is negative 1 over the square root of 2, not rationalized yet. 1 over the square root of 2, positive. Again, not rationalized. But what that tells me is it tells me that this is the cosine of 135 degrees. And if I rationalize that, I get negative square root of 2 over 2. The sine of 135 degrees comes from the y value. Oops, getting ahead of myself. Should show my work. Square root of 2 over square root of 2 gives me 2 over positive 2 over the square root of 2. Positive square root of 2 over 2. Whoa. That one's struggling there. And then I know that tangent is equal to sine over cosine. So I get square root of 2 over 2 over square root of 2 over 2 negative, though. So that means I get negative 1 for my tangent of 135 degrees. That makes sense. I've got a 45, 45, 90 triangle. Opposite over hypotenuse should be 1. But this negative has to do with what quadrant I'm in. So looking at my quadrants, that's not what we want. We don't want that assignment. Looking at my quadrants, well, let's see. These are both to the right. Over here in the first quadrant, cosine's still positive because I'm still to the right. We're still above, so sine is still positive. Quadrant 2, we're to the left, so any cosines are going to be negative. We're still up, so sines are going to be positive because sine's associated with our y value. Quadrant 3, okay, cosines are we're to the left, so our x values, our cosines are negative. Now we're down, so our y values or our sines are negative. And finally, in quadrant 4, we're to the right, so cosine's going to be positive again. And sine, we're still down, so our y's, our sines are still going to be negative. So there we go. That's a breakdown of the unit circle, how we use it. And now we just need to go ahead and apply it to some practice problems on your assignment today.